Welcome, everyone. Today we are going to be looking at a new concept called trig identities. In previous videos, and as well as your homework, you've actually been already introduced to some of these identities, but I thought we would just take a few minutes just as a warm-up to go back and review some of them. So first we'll look at our quotient identity. And the quotient identity is stated as tan theta is equal to sine theta divided by cos theta. So how do we know this is true? Well, we're going to start with our coordinate axes. And we're going to draw a terminal arm here in quadrant 1. And we know from previous videos that we have, this is our point and it's x and y. We know that this side is represented by y. This side along the x-axis would be x. And we've stated that this is our, because remember it forms a circle if we were to rotate this terminal arm around. And so it is the radius of that circle that would appear if we were to just rotate this around the coordinate grid. So we want to prove that tan theta is equal sine theta over cos theta. So let's just take the left side of our equation here, which is tan theta. And we're just going to use our triangle here, and we're going to write tan theta in terms of x, y, and r. So we know tan theta would be our opposite side over the adjacent side. So tan theta would be y divided by x. And let's look at the right side of the equation, which is sine theta over cosine theta. We're going to do the same thing. We're going to rewrite this in terms of our x and our y's. So we know sine theta would be our opposite side y over the hypotenuse, which is r. And cosine is our adjacent side, which is x, over the hypotenuse, which is r. And we know that this, we could write an extra step if you need to. Remember, if we're dividing, we multiply by the reciprocal. And then we could cross out our factors here, and we get y over x. So as you can see, tan theta is equal to y over x, as well as sine over cosine is equal to y over x. Therefore, that means that they would be equal to each other. The other identity that you've seen in other videos is the Pythagorean identity. And I know there was a homework assignment using different values to show the Pythagorean identity. We're going to do the same thing. Let's just redraw our axes down here so we can see it for this example. And the Pythagorean identity states that sine squared theta add cos squared theta is equal to 1. So we'll do the same thing using our triangle here in terms of x, y, and r. So let's look at our left side. So we have sine squared theta add cos squared theta. So we know sine, let's just write our brackets here because we have the squared. So we know sine theta is our opposite over our hypotenuse. Cosine is the adjacent over hypotenuse. So let's rewrite this as y squared over r squared add x squared over r squared, which they have the same denominator, so we could write as y squared x squared over r squared, which really doesn't look like it helps us very much. But think of this word Pythagorean. I'm just going to come back over here to the triangle. And if I asked you to write the Pythagorean relation for this triangle, you would tell me it's side squared, the other leg or side squared, is equal to the hypotenuse squared. So as you can see over here, I have x squared add y squared. I know x squared add y squared is equal to r squared. So I can substitute in an r squared for my numerator here. Divided by r squared is equal to, 1. And if we look at what the right side of our equation was, the right side is 1. So I have 1 is equal to 1. So that means that sine squared theta at cos squared theta is equal to 1. And we'll be using these two identities today in order to do our lesson on just an introduction to trig identities. So the trig identity is an equation involving trigonometric ratios that hold true for all values of the variable. Here are some well-known trig identities. So we've looked at the reciprocal identities previously as well. So secant theta is 1 over cos, cosecant theta is 1 over sine theta, and cotangent theta is 1 over tangent theta, as well as we just looked at our quotient identity here and our Pythagorean identity. Now let's just look at the Pythagorean identity for a minute, because we can rearrange these in case we see them down here in a different form. So if I wanted to solve this, say, for cos squared theta, if I wanted to equal cos squared theta, we would take the sine squared theta, changing the sign to the other side. So we could rewrite the Pythagorean identity to look like this, or we could solve it as well for sine squared theta, which we would bring the cos squared theta to the other side, making it a negative on the other side. So we might see it in this form as well when we're looking for the Pythagorean identities. So we need a few steps or guidelines or a plan in order to approach some of these questions. So this is the plan that we're going to be using here. To simplify algebraic expressions, you may need to perform one or more of the following steps. So first, we're going to look at rewriting all expressions in terms of sine and cosine. We're going to apply these above identities where appropriate. We also might need to common factor or a common denominator, factor or expand as necessary. So we can't forget about those skills as well. So example 1, with a combination of algebraic manipulations and using a known trigonometric identity, express each of the following expressions in a simpler form. So let me just move this up here. I know you'll have that at the first. I'll probably move up and down so we can see our identities as we go along here. So let's look at our first example here. Under this root sign, I see that I have 1 subtract sine squared theta. So first off, write all in terms of sine and cosine. Well, it's already in terms of sine. The next thing I'd look to see if I can apply one of the identities. So when I come over here to the Pythagorean identities, I notice that 1 minus sine squared is equal to cos squared theta. So I can substitute in cos squared theta. Also, if I have a square root, you can rewrite this if you want in exponential form if you choose, but a square root and a squared, remember those are opposite operations and they will cancel each other out, and I have cos theta. So you could, if you wanted to, for your understanding, if you've forgotten this, remember this is sine. We could even write theta like this, and then we could write it to the 1/2. Remember, if I multiply this power of a power, this would be a 1, so just be cosine to the 1. Let's look at our next example. We have tan squared theta subtract secant squared theta. Let's go back to our plan. Rewrite all terms in terms of sine and cosine. So we have some work here to do first. So I'm going to rewrite tan squared theta using my quotient identity of sine squared theta divided by cos squared theta. Subtract, and then I'll use a reciprocal identity for secant squared theta. I know that is 1 over cosine squared theta. As you can see here, we have a common denominator, so we can add or combine the numerators. Apply the above identities where appropriate. So now I see a sine squared theta subtract 1. So I come up here and I have something that looks similar, but if you notice, the one here is a positive, it's a negative here, sign here has the negative, and it's positive here. So I could first factor out a -1. If I'm factoring out a -1, this would now be a positive, and this will be a negative. So I factored out my -1 here. Sorry, I'm just going to come up here to finish this one off. And then I look again and I notice that this is my Pythagorean identity right here, and it is equal to cos squared theta divided by cos squared theta. And then cos squared theta divided by cos squared theta, anything divided by itself will just be 1, and we have our negative here. So my final solution, or my simplified form here, I should say, is -1. So let's look at C. First off, rewrite all in terms of sine and cosine. Well, I have it in terms of sine and cosine. So I would go to my next step and see if I can apply one or more of the identities. So I do see here that I could probably rewrite sine squared in terms of cosine, maybe, and I have a cosine here. And I could write the cosine squared as 1 minus sine squared. But first I'm going to do a little work here because I notice I have 2 terms. And because this is to the 4th and I have a sine squared here, I know I can factor out a sine squared. So my first step here would be factoring out a sine squared of both of these terms. So when I factor it out of the first term, remember we would subtract exponents. So sine to the 4th divided by sine squared will be sine squared theta. And then when I divide it out of this term, the sine squared thetas, they divide to equal 1. So I'm just left here with cos squared theta. Now sine squared theta and cos squared theta is our Pythagorean identity. So I can substitute in for that. And sine squared theta, cos squared theta is equal to 1. And so my simplified answer is sine squared theta. So D. Starting with our steps, I have it all in terms of sine and cosine. Apply one of the identities. Well, the Pythagorean identity has squared. So I notice that I don't have any squareds for this question, so I can't apply a Pythagorean identity to this one. Whenever I have rational expressions, I know I can simplify that by combining the two by finding a common denominator. So that is my first step here, is recognizing that to simplify this, I would want one term, so I'm going to combine using a common denominator. So I'm just going to rewrite this so you can see it a little bit better. So I have this, add this, and I need a common denominator. So to find a common denominator here, we would just multiply these two together. So that means I'm multiplying this by a negative sine theta, and I'll multiply this by a negative sine theta. And this one here, I'm multiplying by a 1 add sine theta, and 1 add sine theta. So when we do this, we can take the cos theta and multiply it by each term in our bracket here. So cos theta multiplied by 1 would be cos theta. Subtract cos theta multiplied by sine theta would be sine theta cos theta. And then when I expand this or multiply these together, if you notice, this is a difference of squares, right? I have a positive and a negative. They're conjugates of each other. And we know if they're conjugates of each other, I will have my first term, which would be 1. And if I multiply my last term, I get sine squared theta. And a negative and a positive here would make it a negative. Let's try our next term. So I'm going to multiply out the numerator. So cosine times 1 is cos theta. Add, and then I have cosine multiplied by sine. So sine theta, cos theta, divided by, and once again, these are conjugates, or you can look at it as a difference of squares here. So I'm going to have my first term subtract and my second term square root of sine squared theta. Now that I have a common denominator, I can combine my numerator. So when I look at the numerator, I'm adding here. So I have cos theta here and a cos theta, so 2 cos theta. And I have a negative sine theta, cos theta, and a positive. So these will actually end up canceling each other out because I have a negative and a positive. Now that I have one term or one expression here, I'm going to look to see if I can go back and use one of the identities. In the numerator, I don't have a squared, so I know I can't apply it here, but I have a squared here of 1 subtract sine squared theta. And if I substitute in, that is cos squared theta. Sorry, I've run out of room here a little bit. Let's just kind of bring it up over here. A cos squared theta and a sine squared theta, this would cross this out, right? We would have 1 cos theta on the bottom. So this is equal to a 2 cos theta as a simplified expression. So example 2, factor each expression. So we're just going back to review before we start our trig identities in the next lesson of just building up some skills here. And we have to remember, because that is one of our things in our plan, is factoring, finding common denominators. So let's look at how we factor these in recognizing our factoring. So when I have two terms, the first thing that should come to mind is whether I have a common factor or a difference of squares. There's no common factor here, but I do have a difference of squares because this is a squared term, this is a squared term, and they have different signs. So remember, you set up your brackets. The square root of 1 will go in the first bracket. The square root of sine squared is the last part of the bracket. And then a difference of squares, that means we have different signs in our bracket. The next example, remember you always look for a common factor. I don't have a common factor in this one, but I do have 3 factors, and it is a trinomial because I have a squared term, and then I just have the cos term, and then I have my constant. So I can factor this as a trinomial. So remember, we look at factors of the first term, which is 1 and 1. So I know this would be a 1 and this would be a 1. The only factors of cos squared theta are cos theta and cosine theta. And then my middle terms have to equal to a -2. So I would need a negative in each bracket because this is a positive, right? A negative and a negative will give me a positive cosine squared theta. And then if I do my smileys, I get a negative cos theta and a negative cos theta for a -2 cos theta. Our next example, we have 2 terms, and I don't have a common factor. So my other type of factoring would be a difference of squares. This is squared. This is a squared term, and they have different signs. So once again, I take the square root of the first term, square root of the second term, sorry for these tiny brackets, and then a different sign in each bracket. Our last example, I have 2 terms. I first look to see if I have a common factor, and I do in this case. I have a sine squared here and a sine here, so I'm able to factor out sine theta. When I factor it out of the first term, I'll be left with sine theta. Sine theta divided by sine theta will equal to 1. So just a little refresher on how to factor when we have trig ratios as part of our expressions. And at the bottom of the page here, you have your homework assignment, which will also be posted under the assignment part on the classroom.